Bismillahirrahmanirrahim. Electrical network analysis, and today we will start a new chapter that is the continuous time Fourier transformation. Okay, so in the previous lecture we have studied the continuous time Laplace transformation, and in this lecture we will study the continuous time Fourier transformation. Okay, so in this transformation, the time domain will be converted to transform to the frequency domain. Okay, so to find the frequency response valid for both periodic and non-periodic. Okay, so this signal is valid for both the periodic and non-periodic. Okay, so t is transformed to j omega. So for this is the formula: f j omega is equal to minus infinity to plus infinity f of t e raised to the power minus j omega t dt. If you can see, it is very similar to that of the Laplace transformation formula. In the Laplace transformation, we have f of s is equal to minus infinity to plus infinity f of t raised to the power minus s t dt. So now the only difference is s is replaced by j omega. Okay, so let's start with the example. So x of t is equal to e raised to the power minus 80 u of t. So I have already uh, discussed u of t function previously, but for a review, so shortly, u of t is just like this. Okay, this is u of t function in which uh, we have the value t is greater than 0, greater than or equal to 0, but no value for the t less than 0. Okay, so this is the of t. It is used for the filtration purpose. Means if you want to get rid of the negative portion of any signal, so multiplying this u of t with that signal, you will get the positive portion of that signal. Means positive portion means you will get the signal only for the t greater than or equal to 0. For example, if you have sinusoidal waveform, okay, just like this, and if you want to get this portion only, so this is t minus t values, these are the plus t values, and this is 0. So if you want to get this portion only, so simply multiplying this with u of t function. Okay, so what will happen? This negative portion will be multiplied with this negative means t negative values. Okay, so after multiplying this, you will get 0, because 0 multiplied by anything is equal to 0. So you are left with only this portion. Okay, and remember, mm, its value is 1. Okay, so it the best thing is that it doesn't affect the magnitude of the signal. Okay, the message signal. So it filtered the signal without disturbing its amplitude. So if you want to get uh, a value on a certain instant, okay, so for this purpose you will use sigma of t, unit impulse function. Okay, and in the next course, that is the signal system, you will studied it in more detail, that there are the shifted versions for u of t and sigma of t. Means you can have the negative portion of this u of t, but by this we will call it u of minus t. Okay, and if you want to get the negative portion of this, for example this, so it will be minus u of t. So u of plus t. Okay, minus u of t. So its amplitude is negative now. So many versions, shifted version of u of t is possible, but this is not included in ENA course. So you will study it in the next course, that is the signals and systems. Okay, so for the time being, uh, we have started the Fourier transformation. Okay, so e raised to the power minus 80 u of t, uh, and we have to find the x of j omega. So e raised to the power minus 80 u of t minus infinity to plus infinity e raised to the power minus 80 u of t multiply by this is the given function, that is f of t, and you have to multiply it with the e raised to the power minus j omega t. Okay, so we are actually using this formula. So minus infinity, okay, due to u of t, you will get rid of minus infinity to 0, so only you will left with 0 to um, 0 to plus infinity, e raised to the power minus at and e raised to the power minus j omega t. The bases are same, so their power will be added. E raised to the power minus a plus j omega whole of t. Okay, so we have taken negative as common. So now applying the integration, so we will get e raised to power minus into a plus j omega bracket over a plus j omega. So the limits 0 to infinity, this is the upper limit, this is the lower limit. Okay, so putting the values of this, okay, this is actually t. So putting the values, the limits in t, uh, infinity, and this is again 0. So you will get minus 1 over a plus j omega into 0 minus 1. Okay, multiplying minus, so you will get 1 over a plus j omega. Okay, so this was very similar to Fourier transformation. Okay, now u of t is equal to x of t dot h of t. So by the transfer function in the Laplace, we call it transfer function, but now in Fourier transformation we will call it the frequency response. Okay, so the frequency response will be the Fourier transformation of the output divided by the Fourier transformation of the input. Okay, so now we have another example. X of t is equal to cos of cos at. Okay, so for find the Fourier transformation. So the simple method to solve it is that e raised to power, so you have to split it in exponential formula. Okay, so this is the exponential version of the cos of 80. So we have studied it in the mathematics that both of the sine and cosine functions can be converted into the exponential functions. Okay, so e raised to power 80 plus e raised to power minus 80 divided by 2, this is equal to cos 80. Okay, so right over here, now applying the Fourier transformation, so you have to multiply it with e raised to power j omega t on this and this as well. Okay, so the bases are same, their power will be added, so you will get e raised to power minus a plus j omega whole. So the limits are from 0 to infinity on both of these functions. So putting the limits infinity and 0, so you will get, minus 1 over 2 into 1 plus over 1 over a plus j omega plus 1 over 2 a plus j omega. Okay, so 1 over 2 common. Okay, so you will get, this is a minus j omega. Okay, this is a plus j omega. So that was all about the cos of 80. Okay, now we have another function, that is f of t is equal to t. So applying the Fourier transformation, t dot e raised to the power minus j omega t. This is there is an error. This is not s. This is j omega. Okay, because this is Fourier transformation, not the Laplace transformation. So 0 to infinity t dot e raised to the power minus j omega t dt. So now we have no other way. We have to apply the integration by parts. Okay. So integration by parts, the formula for the integration by parts is first into integration of second minus integral differential of first into integration of second, differential of first into integration of second. Okay, so this is the whole integration bracket. Okay, so first we have to find this, then this, and at the end you will solve this bigger integration. Okay, so that is the method for the integration by parts. So you have to take one, that function which can be decay, which can be uh, dissolved to one by applying the derivative. Okay, so t can be dissolved to one by taking the derivative of t, dt by dt, this will be equal to 1. Okay, so this is a technique. So we have to consider it 1 and this is 2. Okay, so first into integration of second minus integral differential of first integration of second. We have solved this derivative which is equal to 1. Solve this integration, you will get this e raised to power minus j omega t over minus j omega t. Okay, t, and solve this integration as well, e raised to power minus j omega t divided by minus j omega t. Okay, now putting the limits 0 to infinity, 0 to infinity after solving this integration. Okay, so don't let the solution to infinity. Okay, so you have to uh, do some arrangement so that the answer cannot be moved towards the undefined case. Okay, we have to avoid the undefined case and applying some techniques or rearrangement so that the solution is moved to the some limited finite value. Okay, so by putting the values, okay, you will get 1 over j omega whole square. Okay, if you remember the in the Laplace transformation, the Laplace transformation of t was 1 over s square. Now in this case we have 1 over j omega whole square. Okay, so if you solve this, j square is equal to minus 1, so it will be minus 1 over omega square. Okay, x of t is equal to 2t. So again, this is not 2t, this is u of t. Mm, this is u of t. Okay, u of t, this is u of t. Okay, so u of t 1, its magnitude is 1. Okay, and this e raised to power minus j omega t. So it is very simple, 1 multiplied by this, and due to unit step function, the limits will be from 0 to infinity, because it have 0 value for t less than 0. Okay, so that is why limits will be from 0 to infinity, and solving this integration you will get e raised to power minus j omega t over minus j omega from 0 to infinity. Putting the limits in t, you will get e raised to the power of minus infinity minus e raised to the power 0. So you will get 2 divided by j omega. Okay. Now the transfer function. Okay. Okay, this is another example, e raised to the power 4t. So f of t is equal to e raised to the power 4t. So e raised to the power 4t dot e raised to the power minus j omega t. Okay, this is actually dot. So the bases are same, their power will be added. It is very simple. So you will get 1 over j omega minus 4. Okay, now the frequency response. So as I have told you in the previous slide that the Fourier transformation of the output quantity over the Fourier transformation of the input quantity, this will be equal to the transfer function. Sorry, the frequency response. Okay, we call it frequency response in Fourier transformation. So Fourier transformation of this y t is equal to dt by dy by dt. Okay, so y of j omega is equal to j omega dot x j omega. Okay, applying the Fourier transform, as we know that the Fourier transformation of d by dt is equal to j omega. Okay, remember it, it is j omega. So y of t, this is converted in applying the Fourier transformation, you will get y of j omega. Now d by dt, the Fourier transformation of this will be j omega, and x of t, it will be x of j omega. Very simple. This is output, this is input. So output divided by input is equal to j omega. So this is the transfer function. Okay, very simple. This is the transfer function. Okay, now convolution. X of t is equal to e raised to the power minus at, and h of t is equal to e raised to the power minus bt. So it is very simple, similar to that of the convolution we have studied in the Laplace transformation. So y of t is equal to x of t into h of t. X of t is e raised to the power minus at. H of t is equal to e raised to the power minus bt. Multiplying the applying the Fourier transformation, you will get y of j omega is equal to 1 over a plus j omega into 1 over b plus j omega. Now the partial fraction. Okay, so that we can find the h of t. Sorry, y of t. Okay, by inverse Laplace transform. So we have already gone through this process many times, that we have to apply the partial fraction, taking the LCM, multiplying this LCM on both sides, and followed by finding the values for the A and B. So for A, put j omega is equal to minus A, so that the B term will be 0. Okay, so that we can be able to find the value for the A. So this is the method. Now for the B, put j omega is equal to minus B. Putting the values, you will get B is equal to 1 over A minus B. Okay. So now we have both the A and B values. Just put it over here in this equation. So you will get this. Okay. Taking 1 over B minus A common. So you will left with 1 over A plus j omega minus 1 over B plus j omega. Applying the inverse Laplace transformation, so you will get e raised to the power minus 80. If this is plus, so it will be minus. Okay, there is a mistake. E raised to the power. Oh no, it has been mentioned, but it 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 is not that much seeable. Okay, so e raised to the power minus 80. This is b e raised to the power minus bt. Okay, so this is the answer, and this is the answer. This is the solution of the y of t after the convolution using Fourier transformation method. Okay, so do practice on these questions, and if you have a clear idea of the Laplace transformation, so then you will be able to easily solve the Fourier transformation. Okay, so thank you. We will discuss the remaining portion of Fourier transformation in the next lecture. So thank you for that moment.